Hello, good afternoon, everybody. Today we are continuing with the construction of bode plots, and we have seen that the bode plot consists of two plots, the magnitude plot and the phase plot. And the first step is to convert the transfer function into its time constant form, and then finding the steady state gain k from the time constant form. So that k is very important parameter, and then you need to find the corner frequency of each terms. We know that for a first order term the corner frequency is 1 by tau, and the corner frequency for the second order term is omega n. So after finding the corner frequencies, and then we are moving towards the another rule, that is initial slope line of magnitude plot. So we know that the magnitude plot is the magnitude in dB versus log of W. Okay, this is the magnitude plot. Now, so we also note that the importance of the corner frequencies. So let's say these are the corner frequency CF1, let's say this is CF2. Okay, so at this frequency the slope of this magnitude curve will change. So let's say if this is the slope, then from this the slope will change. Let's say this to change, it will continue till this, then let's say the slope is changing. Okay, so at this corner frequencies the slope is changing. Note that this is a negative slope line and this is a positive slope line. We have also seen how to draw plus 20 dB by decade line. We have also seen plus 40, minus 40 dB per decade slope line, plus 60, minus 60 dB per decade slope line. We have already practiced that. Now, this rule says that about the initial slope line of the magnitude plot. So I'm talking about this. This is the initial slope line. Okay. So what is the slope of this line? The initial slope line. So once I know the slope of this line, then at every corner frequency there is a change in the slope that we will see later on. But I should know the starting point of the magnitude plot. So this is about starting point or starting line of magnitude plot. Okay. So we are going to discuss this rule, that is initial slope line of the magnitude plot. All right. So there is a rule for that. The rule is something like this, that type of the system and initial slope line. Initial slope of the, initial slope. So I need to understand this step. We know that what do you mean by the type of the system? Type of the system is how many number of poles at origin inside the S-plane. So if let's say this is the system, G of S, H of S, then there is a one pole at origin, so it is type 1 system. If it is this, then type 2 system. If at all there is no pole at origin, then it is type 0 system. Okay, so we know based on the number of poles at the origin, we can define the type of the system. So now, so for type 0 system, the initial slope line is actually 0 dB per decade. Okay, so what is 0 dB per decade line? A slope having 0 dB per decade line is actually a horizontal line. All this line is having 0 slope. Okay, so it is a horizontal line, or you can say parallel to omega axis, or you can say log omega axis. Okay, so if this is the log omega axis, then this is all these lines are 0 dB lines. Okay, because the slope is 0 dB per decade. Now, sorry. Now, if it is type 1 system, then the slope is actually minus 20 dB per decade. The initial line is having the slope of minus 20 dB per decade. In 1 decade, the magnitude will change to 0 to minus 20 dB. If it is type 2 system, then it is minus 40 dB per decade. Okay. If it is type 3 system, then minus 60 dB per decade. So now you can generalize this. If it is nth type system, then the initial slope line is minus n into 20 dB per decade. So this is about the initial slope line. Now this was the case when a pole was at origin. It may happen that there is a 0 at origin. In the transfer function. Means the transfer function is something like this. Something like this. So now here there is a 0 at origin. Okay. So if there is a 0 at origin, so let's say 1 0 at origin. You cannot say type 1 system, but you can say 1 0 system, then it is plus 20 dB per decade. So instead of minus, the slope is plus. So instead of minus, the slope would be plus. Okay. If there are 2 zeros, then it is 2 plus 2 into 20 dB per decade. If let's say there are n number of zeros or m number of zeros, then you can say plus m into 20 dB per decade. So this is how the initial slope line can be computed. So hope you understand that if it is type 0 system, there is no pole at origin, then 0 dB per decade. But let's say if there is 1 0 at origin, plus 20 dB per decade. 1 pole at origin, minus 20. 2 pole at origin, there is s square atom in the denominator, then this. Okay. Now the question is, after computing the initial slope line, let's say this is the log W, and this is in decibel, that is magnitude. Okay. Now so once you know that what is the initial slope line, so let's say initial slope line is minus 20 dB per decade. So this is minus 20 dB per decade line, but this is also minus 20 dB per decade line. This is also minus 20 dB per decade line. So which line I need to choose, or from where I need to start? Okay. So if I know that the initial slope line, whether this, if it is crossing the 0 dB axis, so this is 0 dB axis, okay. This would be plus 20 dB, this would be plus 40 dB, this would be plus 60 dB, something like this. Now, if the initial slope line, which is crossing the 0 dB axis, this is 0 dB axis, or you can say log omega axis. If I know that the initial slope line crossing the 0 dB axis at any point, at any omega, if I know this, then I can compute this line. Okay. I hope you understand that, let's say, this is the initial slope line. it crosses here. Okay. Now if I know this point, now this point is W. Okay, any W. Now if I know this W, that this is initial slope line. Right now we are focusing on the magnitude plot only. Okay. So the phase plot we will discuss later on. So this is the initial slope line, and if I know that initial slope line crossing the 0 dB axis at omega, then I can draw a line which is passing through this point whose slope is, let's say, minus 20 dB per decade. Okay, then I can draw. So all these are having minus 20 dB per decade, but they are crossing at different omega. But if I know that where the initial slope line will cross the 0 dB axis, if I know this, then I can draw the initial slope line. So let us understand in the next rule that the initial slope line crossing the 0 dB axis at what value of omega? So the rule is something like this, that initial slope line crossing 0 dB axis at what omega? Okay, if I know this, that the initial slope line is crossing the 0 dB axis at omega is equal to something, then I can draw from that point the initial slope line. Okay, so for that there is a rule. The rule is something like this, that type of system, okay, and initial slope line crossing 0 dB axis at omega is equal to, okay. So if the type of the system is zero type system, there is no pole at origin, or there is no zero at origin, type 0 system. Okay. If it is type 0 system, there is no pole at origin, there is no zero at origin. Okay, then we know that the initial slope line is the parallel, so it will not cross the 0 dB axis. Okay, so it will not cross, because parallel lines doesn't cross each other. Okay. Okay, if it is type 1 system, then if it is type 1 system, the initial slope is minus 20 dB per decade. So minus 20 dB per decade line that will cross the 0 dB axis at omega is equal to K. Okay, what is K? K is steady state gain computed after time constant form. Okay, so we have been given G of S, H of S. This is given to us. We need to convert into a time constant form. Then whatever the K is left there, that is the steady state gain. For example, it is 10 upon S plus 9. This is the transfer function, 10 upon S plus 9. So this is not in time constant form. Time constant form is in the form of tau S plus 1. So I need to convert it to time constant form. 10 upon 9 is common. So S by 9 plus 1. So this is 10 by 9 divided by S by 9 plus 1. So this is in the form of K upon tau S plus 1. So what is K? K is 10 by 9. So I am talking about this K. Okay. So if it is type 1 system, the steady state gain, the initial slope line will cross the 0 dB axis at omega is equal to K. So if you compute the K wrongly, then this would be wrong, and your entire magnitude plot would be wrong. So that's why I'm saying repeatedly that convert the transfer function into a time constant form correctly. Now, if let's say it is type 2 system, then it will cross the 0 dB line at omega is equal to root of k. Okay, or you can say k raised to 1 by 2. Okay, if it is type 3 system, then it will cross at cube root of k. Okay, or you can say k raised to 1 by 3. If let's say it is type n system, then it will cross the 0 dB axis at nth root of k. Okay, so you can say k raised to 1 by n. Now it may be possible that there are some, so this was about poles at origin. Okay, but it may happen that there can be a zeros at origin also. So see, first of all, either pole at origin or zeros at origin, both cannot be occur because they may cancel out. The numerator term can be cancelled out with the denominator term. Both cannot happen simultaneously. So now if it is zeros at origin, then what is the scenario? So let's say 1 0 at origin. So I'm talking about s in the numerator. Okay. Then it will cross at 1 by k. Okay. If there are two zeros at origin, then it is 1 by root of k. Okay. If there are n number of zeros at origin, then it is 1 by nth root of k. This is the situations. All right. So far we have discussed the initial slope line of the magnitude plot. That what is the slope of the initial slope line? That is one thing. And the initial slope line with that particular slope will cross the 0 dB axis at what omega? At what frequency? So we have seen that two rules. All right. Now I need to prepare a table. The table is something like this. All right. So first of all, before preparing the table, arrange all corner frequencies in the ascending order. It means that the corner frequency 1, corner frequency 2, corner frequency 3, and so on. Okay, you need to arrange all the corner frequencies in the ascending order. Means the corner frequency 1 should be the lowest and corner frequency 3 should be the largest, or you can say smallest and largest in this way. So CF1 is smallest, CF2 is larger than CF1, CF3 is larger than CF2 and CF1. So you need to arrange the corner frequencies. Okay. Now you need to prepare the table. The table is something like this. Terms. Okay. Then you write corner frequencies. Okay. Then slope contribution. And then final slope. This is how you need to prepare a table. One is the terms. So I'm talking about these terms means transfer function terms. So let us understand the meaning of all this first, and then we will prepare the table. Okay. So right now, So let's say if this is the system k upon s plus 2 s square plus 2s plus 8, for example. This is the transfer function. If this is the transfer function, then the terms means k s plus 2 in the numerator, 1 by s square, 1 upon s square plus 2s plus 8. These all are terms. So I have 1, 2, 3 and 4 terms in these transfer functions. Okay. We will not actually consider k as a term. It is a steady state gain after converting into a time constant form. Okay. All right. So these are all terms. So a transfer function can be made from different terms. So this is a first order term in the numerator. This is a second order term, s square. This is a second order term. This is also a second order term. There can be another term also. Let's say s plus 5. This is also another term. A first order term in the denominator. Okay. So the transfer function may have a poles at origin or the zeros at origin or a first order term on the numerator or the second order term on the denominator or the second order term on the numerator or the first order term on the denominator. So the transfer function is composed of first order terms and second order terms. Okay, that is the thing. It cannot be having third order term, because if it is having the third order term, that can be break into 3 first order terms, or it can be break into 1 first order term and 1 second order terms. Okay, so I'm talking the terms means this. Now each and every term is contributing the corner frequencies. Now we know that the steady state gain doesn't contribute in the corner frequency. Okay, what about a pole at origin? A pole at origin or a zero at origin, maybe multiple poles, that doesn't contribute in the corner frequency. So corner frequencies that doesn't come from a pole at origin or this. So corner frequency comes from first order terms and standard first order terms and standard second order term. This is a second order term, but the pole at origin, it doesn't contribute the corner frequencies. There can be second order terms also. So the corner frequencies from this term is 1 by tau. Corner frequency from this term is omega. Corner frequency from this term is also 1 by tau. Okay. So we need to find the corner frequency of each terms. Then about the slope contributions. Now, the steady state gain. So now I'm talking about the slope contribution. Okay. We have discussed the corner frequencies. Once again, let me summarize. Corner frequencies are contributing from first order terms and second order terms. Okay. From first order term, the corner frequency would be 1 by tau. For a second order term, the corner frequency would be omega. Okay. Corner frequency for steady state gain k, there is no corner frequency. For 1 by s square or s square, a pole at origin or a zero at origin, there is no any corner frequency. Okay. All right. Then about the slope contribution. Now for the slope contribution, the steady state gain k term doesn't contribute any slope, so there is no slope for k. For a first order term, in the numerator, it is in the numerator. So if the terms are in numerator or due to zeros, the slope is always positive. Okay, and terms in denominator, that is from proles, the slope contribution is always negative. Okay, so this is in the numerator, a first order term. A first order term will contribute plus minus 20. A second order term will contribute plus minus 40 dB per dB. Okay, dB per decade. Slope contribution. So contribution of this term for a first order term in the numerator would be plus 20. This is a second order term in denominator, so it would be minus 40 dB per decade. This is in the denominator, 1 upon s plus 5 in the denominator side. So the slope contribution would be minus 20 dB per decade, and so on. Slope contribution for this 1 by s square There are two poles at origin, so it is a second order term, so it is minus 40 dB per decade. Okay. All right, we'll continue with this table in the next class. Thank you.